Chapter 9, Electrons in Atoms and the Periodic Table. Not electrons in the periodic table. We're talking about electrons in atoms. And we're talking about the periodic table. You guys heard of the Hindenburg? 1937. There's a picture of it. So they made this large airship, this dirigible, a blimp, if you will, and they filled it with hydrogen gas. Hydrogen is flammable. They made it across the Atlantic, and as they were landing, this happened. Not good. Amazingly, only 36 of the 97 passengers were killed. Now we fill them with helium. Hydrogen works better. It has more lift than helium does, but it has this disadvantage of being very flammable. And the reason that we bring this up at all is why? What makes hydrogen so reactive? Why is hydrogen flammable? Why does it burn? We're still using blimps. You know, they fly over the football games, and but now they fill them with helium. Helium's better because helium doesn't burn. Why? Why doesn't helium burn? These are questions that hopefully we'll be able to answer at the end of this chapter. So we're going to learn about models of the atom that help us to explain things like this. And then we can ask ourselves, well, what about the other elements? Are other elements as reactive as hydrogen? If we look at the other group 1 elements, lithium and sodium are in group 1 with hydrogen. They are also very reactive. And if we look at helium in group 8A, he's one of the noble gases. The other noble gases, neon, argon, krypton, radon, forgot one, xenon. Those guys are also very inert. And so we see this common behavior among elements that are in the same group, the same column in the periodic table. And the models and theories we're going to talk about in terms of models of the atoms are going to help us to explain why that is. So we're going to look at two important models. The Bohr model, which came first, and then the quantum mechanical model. Remember, models or theories propose explanations. Laws say what happens. Theories and models help us to understand why, and they help us to predict what might happen in the future. So these help us to also understand the periodic law. The periodic law is this: when the elements are arranged in order of increasing atomic number, certain sets of properties recur periodically. That's why it's called a periodic table, because there are patterns that repeat periodically. And that's why the group 1A elements are all stacked up on top of each other, because they have a lot of common properties. So the models we're going to talk about help us to understand how electrons exist in atoms, what are they doing, and how do those electrons affect the chemical and physical properties of elements. Now, quantum mechanics is something that is hard to get your mind around because it only applies to very, very small objects, objects that are way too small to see. And so it doesn't apply to things like baseballs or cars crashing into walls or anything like that. So it's hard to get our minds around it. And we're not going to go real deep into it in 3A. We're just going to learn enough to help us understand what's going on with the periodic table. But here are some what I find very interesting quotes from 3 of the major scientists that were involved in developing the quantum mechanical model of the atom. Niels Bohr said, "Anyone who is not shocked by quantum mechanics has not understood it." Erwin Schrödinger said, "I don't like it, and I am sorry I ever had anything to do with it." And Albert Einstein is quoted as saying, "God does not play dice with the universe." The quantum mechanical model is essential, it's foundational to modern chemistry. It helps us to understand chemical bonding. It's the basis of the modern periodic table. And because of the quantum mechanical, we are able to apply what we know and make things like semiconductor devices, which are essential to computers and tablets and cell phones and things like that. And also helps us to understand how we can design new drugs instead of just haphazardly coming across them. Did you ever wonder, how did people find out that if you chew on the bark of this tree, it'll make your headache feel better? Were they just so desperate they went out and tried everything? I think, a lot of that was chance and trial and error. And how many people died trying poisonous things, right? It's not a real effective method. When we understand how atoms bond together and how it affects their properties, then we can design new drugs much more efficiently to target certain things and not harm the body. So it's a really good thing.